So today I'm going to wrap up the first part of the subjects that will be covered on the first test. And this first part will be about autoencoders, and then I'm going to go a bit more general and talk about representation learning and how it relates to transfer learning that we saw last week. So first I'm going to explain what are autoencoders and talk about different restrictions for obtaining the encoding. Talk about convolutional autoencoders that you can apply to images. This is a particular example of autoencoders. And then talk a bit about some applications. But first, let's see what an autoencoder is. This is basically a network that is trained to output something that is as close as possible to the input. This means that we can train it unsupervised. From our perspective, this would be unsupervised learning because we just put in all the data that we have. We don't need labels, and the network learns with that data. Of course, from the perspective of the network and backpropagation and all that we've been seeing so far, this works exactly as all the networks that we saw, in that we have a loss function here, for example, mean squared error or something like that, and we want to minimize that loss function by adjusting the weights. So from the perspective of the network, this works as supervised learning. From our perspective, it's unsupervised learning because we don't need labels, since the output is the same as the input. Now the question is, why do we want something that outputs the same as the input? Before exploring that, let's break down this network and consider the idea that we've been seeing so far, which is that the deep neural networks are learning representations of the input, and they are changing the representations along the network. And so we can imagine that the first part of our network is changing these representations until it obtains some kind of encoding. And then would be the encoder. And then the second part, the decoder, is reversing those transformations until it goes back to the original input that we gave the network. So the autoencoder we can imagine to be an encoder followed by a decoder that makes some transformation, reverses that transformation, brings us back to the beginning, and now it's what's happening inside the network that is important. So basically the idea is, why do we want to learn a way to decode some encoding just to get back the x which we already have? So if we already have x, why do we want to find a g of f of x that gives us x again? This by itself would not be very interesting, but the interesting things about the autoencoder are in the encoder and the decoder, and those are the elements that then we can use. So basically we are learning to transform our inputs in some latent space here, represented by the encoding inside the network, in a way that allows us to recover the input, the original input, after we start from this encoding, if we do suitable transformations. So the idea is that this is an encoding of the input that has the necessary information to recover the input as well as possible. So basically autoencoders work in an unsupervised manner from our perspective because we don't need any labels, and they are useful to create these representations and to train these encoders and decoders. There can be several advantages of the latent representation, so we're going to focus on that first. They can be, for example, of a lower dimension. They have to capture structure in the data because they must allow the decoder to retrieve the original data from that more compact representation. So they can allow data compression or separating different types of features and things like that, depending on what we force the autoencoder to do. So basically what we can control here is applying restrictions to this encoding so that the encoding has the kind of characteristics that we want it to have. So usually autoencoders are feed-forward networks. You can create autoencoders with recurrent networks, but I'm going just to use these feed-forward networks as examples. They are trained with backpropagation like the other networks, because from the perspective of the network, this is simply minimizing the loss function as usual. Since the target is the same as the input, we don't need labels. So for us, it works like unsupervised learning. What we really need is to create some constraints, some bottleneck on the encoder, so that the network does not just have to copy the values trivially from the beginning to the end, and needs to do something that is useful. Now, what is useful, this depends on what we want, but it has to be something that captures the structure of the data and provides good features in some sense that we can then define depending on the pressure we are putting on the encoder. Okay. We're going to see a bit more on this, the idea of useful representations in the next lecture, but the next lecture will be a bit more abstract. This one, we're going to focus specifically on autoencoders. So let's see some different types. A very simple autoencoder to understand and very intuitive is the undercomplete autoencoder. So basically, this is one where the latent space, that inner part of the autoencoder where we have the representation we want, has a lower dimension than the original input, and so the output of the autoencoder too. So basically, it's something that squeezes down in the dimensions and then goes up again. This is trained by minimizing the loss function that is comparing the input to the composition of the encoder of the input, this f of x, and then followed by the decoder. So the encoder is going to compress the input into a lower dimension. The decoder is going to retrieve the original input, and now we're going to compare this to the original input, and this is what we want to minimize. For example, a mean squared error between the input and the output values. If this was just a linear transformation, then it could be something similar to PCA, trying to squeeze everything into a lower dimension. Although we don't have the orthogonality constraint that principal component analysis has, in which the eigenvectors are all perpendicular to each other. But since we are using deep neural networks, we can go very much beyond linear. We can have very deep networks that do complex transformations. So we have a lot more power to decide what transformations, how much these things are transformed. And so we can transform the data into a representation in a much more powerful way. However, note that we always have this problem of overfitting, and imagine that we are compressing everything to a single value, and the decoder has so many parameters that it just stores all the possible outputs in the training set. So basically this value is acting as an index in a lookup table. If it's pattern number 1, it outputs something. If it's pattern number 2, it outputs another thing, and so on. So if you reach that point, there's a lot of overfitting, because this will only work for the training set. The value itself in the encoding has no meaning, and if you use something that is outside the training set, it will probably not generalize. So we must be careful not to use a network that is too powerful, so that we force the autoencoder to capture something that is useful and meaningful in the data in the encoder, in a way that can be then recovered in a generalized way that can be applied to other examples too. This is a classical example of an autoencoder by Mitchell, so this is from the 90s. These are the possible inputs, so vectors of 1 followed by zeros, or 0, 1, 0, and so on. These are, the input has a dimension of 8, but the training set only has 1, 1, and the rest are zeros. And these are the possible examples in the training set. So we want to train the network to output the same vectors with dimension 8, but the hidden layer of the network only has 3 neurons and not 8. So it must reduce from 8 to 3. And what we have here, the activations of these 3 neurons for the different patterns in the input correspond to a binary representation of the 8. So we have 101, 001, 010, and so on. They are not in order because the network chooses the order depending on the initial weights and the ordering of the examples and such. But we have the 8 possible combinations of 3 neurons here that activate differently for the different inputs so that the outputs can then be reconstructed. And this is a simple example of an autoencoder finding an encoding that captures some structure in the data by forcing it to reduce the number of dimensions in the data. There are other possibilities if we use regularization. So this would be an example of an overcomplete autoencoder in which we even have more dimensions in the encoding than in the input and the output, which by itself would not be useful because there would be many trivial ways of doing this transformation, just copying the values here, so the encoding itself would not be of use. But the idea is that we do not need to shrink the dimensions in order to get something useful if we impose other constraints. And we can do that by regularization. For example, in a sparse autoencoder, we try to force the autoencoder not only to reproduce faithfully the input, but also to have a small number of activations in the hidden layer, in that representation it's created. So let's measure this, average activation in the hidden layer by summing the activations of the neurons in the hidden layer for each example. And dividing by the number of inputs we have there. And this gives us, for a particular example, we can say how many activations occurred, and we can average that for our examples. And if we put this value, the target value here, low, for example, 10%, we are trying to force our autoencoder to create representations of the examples that we input, but only activating a small percentage on average of the neurons there, for example, 10%. So the way we can use this is to add to the loss function that we have. This is what is forcing the autoencoder to output something that is similar to the input. But with some weight, we add this regularization term, that is the divergence between what is the average activation of the hidden layer of that latent space neurons for the examples we are presenting, and the target that we want. So if this is the same, so basically this is the Kullback-Leibler divergence is a way of measuring the difference, so to speak, between the probability distributions. It depends on what the distributions are, but for this particular case, it would be this expression. And if the two are equal, so if on average our latent representation is activating the fraction of neurons corresponding to our target value, then this would be the logarithm of 1, so this would be 0, and we wouldn't penalize anything. But if it's different from the target, then we start penalizing and we force the autoencoder to change the parameters. So basically what we are forcing here is the autoencoder to be able to reproduce the input, but only firing a few neurons at a time. And as we give some examples, it will only fire a few neurons. And this is something that's actually similar to L1 regularization, or if we look at it in a Bayesian perspective, it will be using this Laplace prior, which corresponds to adding a penalty on the absolute values of the activations, which is similar to what we saw for L1 regularization, but note that we are not applying this regularization to the parameters, as we typically use with L1 and L2, but we are applying this to the activation of the neurons. So it's not the weights themselves that we want to shrink down, it's the activations of the neurons that we want to reduce. So this is an example. This is a sparse autoencoder trained on images of 10 by 10 pixels. And in the latent representation of the autoencoder, so at the midpoint of the autoencoder, we have 100 neurons. So images of 10 by 10 have 100 values. At the middle we have 100 neurons, which is the same dimension, but we impose the restriction of trying to minimize the number of neurons that are firing for each example. If I recall correctly, this was 0.1 or 10%, but I'm not sure. You can check the paper, but the result is that the different neurons in the hidden representation are specializing in different characteristics of the images. So we have these kinds of bright diagonals on the edge, or verticals, or horizontals, things like that, in a way that for each image in the examples, only a few of these features are present. So for each image, only a few of the neurons fire, and different combinations of neurons are firing for different images, which is what allows the autoencoder to reproduce the original. And basically, this makes the representation in the latent layer of the autoencoder focus on specific attributes of the inputs that allow us to distinguish the different inputs. And this is one example of how we can constrain this representation to give us something useful. These are examples of sparse autoencoders trained on NIST with different penalties. So if we don't apply a penalty, we have something that is very confusing, doesn't seem to capture much of interest. But with these kinds of penalties, for example, this Kullback level of divergence I mentioned, we see that different neurons are specializing on different kinds of curves that we find in different digits. So this NIST dataset, if you recall, is the one of the handwritten digits, and we see here neurons that are firing for something that looks like a 9, others for something that looks like an 8, and something that looks like a 1, and so on. So they are capturing patterns that appear there, and each neuron specializing on a particular pattern to help distinguish these examples. Another thing that we can do to train an autoencoder is to force it to reconstruct the original input, but we don't give it the original input, we give something that has been degraded, for example, by adding random noise. So now the autoencoder cannot simply copy the input into the output, it must also figure out, so to speak, which parts of the input are the noise and which parts are the signal, and filter out the noise to recover the signal. So denoising autoencoders this is a trick to make the encoding more robust to variations in the input, because there will be lots of examples here that must have the same output. It's just the same example degraded in different ways. This addition of noise is also something that we saw in regularization that effectively increases the size of the data. But basically, with denoising autoencoders, we have this very simple way of forcing the autoencoder to learn something useful. And this, in fact, can be combined with others. It can be undercomplete and denoising and sparse, if you want. You can combine all of these things.
Professor?
Yes?
Good question. Is it already trained with denoised data, or we just train it all with noise?
Yeah, usually in denoising autoencoders, you start training also always adding noise. So you always add noise to the data, and you want it to learn to recover the original. This is the general approach.
Okay.
So it's also learning to remove noise from there. And that could be one application. One application of this would be cleaning up noisy data. You train it with by adding noise to data that you know has no noise, but then it can perform with noisy data.
So we already trained it previously without noise?
No, you have the data without noise, but you are training it always with noise. You need the data without noise because you need this to be your target. You cannot have a noisy target here. But if you train the autoencoder to denoise this data, then if you have data that has noise, not that you added, but it's noisy by itself, then this can work and denoise that data too.
Okay.
So it can be used as a filter to remove noise from data, for example. But basically, this forces the autoencoder to learn something about the distribution of the data by abstracting what is important from the noise. And this is very simple to train, because you just need to apply corruption with some probability, and then you want to minimize the difference between what you have on the output of the decoder and the original image there, or the original input. You're adding an input with noise, but you want to compare the output with the original. There's something that works similar, the contractive autoencoder, but this one is adding a regularization term that is proportional to the magnitude of the derivative of the activations in the latent layer, in that hidden layer that we are looking at the representations in, with respect to the inputs. So basically what we want to do is to make the encoding that the autoencoder is producing insensitive to small variations of the input. If the small variations of the input create large changes in the encoding, then these derivatives will be high and there will be a large penalty here. If small variations in the input lead to small or nearly null variations on the encoder, then this would be very small and has less penalization. So when we combine this with the loss function, we're trying to recover the original input. What we end up with is an autoencoder that has a representation that is less sensitive to small variations on the input, and also puts together, close together on the representation, inputs that are similar. And that's why it's called a contractive autoencoder, because you can imagine it shrinking the space of representation so that the inputs are all similar, and the more similar the inputs, the more similar the representation it will have. This will also favor smaller weights, so it also acts as regularization in that sense, because if we have smaller weights on the autoencoder, these derivatives will generally tend to be smaller. But note that we are putting this in with a small fraction there, and we are always forcing the autoencoder to reproduce, to recover the original image from the encoding, or the original input from the encoding. So the autoencoder must be able to bring back the original input with that restriction of trying to minimize those derivatives. Yes?
So H here is still a probability of a neuron firing? Or
No, this is just the activation. This is the derivative of the activation of the neuron in that encoding layer with respect to the inputs. Okay, so it's not a probability; it's the activation value there. You chain all the activation function, the neurons on the previous layer, and so on, all the way to the input, and you compute that derivative. Okay? So if this derivative is high, it means that a small change in the input will lead to a large change on the representation that the network is learning, and that is penalized. If it's low, it means that the network doesn't change much the representation when you change a bit the input. And so it brings together similar examples into the same region on the representation space, and that's why it's a contractive autoencoder. This is actually similar to, the effect is similar to the denoising autoencoder, because the denoising autoencoder also forces similar representations to slightly different inputs. It tends to be more expensive to compute. So it's less expensive to just add noise than to compute all of those derivatives. So in general, denoising autoencoders are more often used than this one, but this is another example of how you can push the way the autoencoder creates representations in order for those representations to have characteristics that you want. This is actually, this is a bit complex the way they compute this. If you want to see the details, you can look at the paper. But the idea is that they use contractive autoencoders to create a more compact representation of the MIS dataset and the CFAR dataset. This is an image dataset of small color images. And they compared the way a classifier trained on those representations worked with the way the classifier would work on PCA reduction to the same dimension. And what is represented here is basically the directions of the input. So you can imagine that this image is a point in a very large dimensional space, and you can find the principal directions of this input that will change the value of the loss function, that have the largest impact on the value of the loss function. And if we are using the representations created by the contractive autoencoder, it's actually using things that seem to make sense. So it's following those lines on the zero, or some patterns here on the image of the horse. But if you do the same thing, and instead of using the features learned with the contractive autoencoder, using those learned from PCA, basically the network is now looking at some apparently random set of pixels to determine what class it's going to put the image in. So the idea here is that the contractive autoencoder is capturing better the structure of the data and the way the examples relate to each other, and how then we can divide the different classes in that representation will be more meaningful than if we just do something like the PCA. Okay, so I've been talking about these examples with images, but usually with images we use convolution layers because of the way the patterns of importance in the image can be found in different positions of the image. And so you can use autoencoders with dense networks, but usually for images we're going to use convolution autoencoders. And this is something similar to the problem we saw last week for segmentation, which is we are applying convolution and pooling and creating this latent representation, and then we need to upsample again, or to recover the original resolution so that we recover the original image. Last week we saw this problem with segmentation, so that we have a feature map on the output that has the same resolution as the input and can give us the shapes, the masks for where the different objects are in our image. But now what we want is to actually recover the image itself. So we're going to look again at these options for going up on the resolution here. We already saw this part. You do convolutions and pooling, and there are several different options for this part here, for the decoder. So you have, for example, in Keras you have transposed convolution. There are possibilities like fractional stride convolution too, but usually upsampling with nearest neighbor or interpolation and convolution seems to be the best approach. So I'm going to talk a bit about the problems with the first ones when you are actually trying to recover the original image. So to recall here, this is what you get with a convolution in one dimension, to simplify. So this is the vector of data we have here. And when we apply a convolution, we have a kernel, and we're going to slide it over the input with some stride. So in this case, we have a stride of 2. We can also use padding. Here we have a padding of 2 zeros, so that we can start here with the kernel, but you can control this. And this would be the output of the convolution. So we are applying this kernel to these values here. We multiply each value by each weight in the kernel. We add everything, and we have this on the output. And then we slide the kernel, and we repeat that. And depending on the stride that we have here and the padding, we will have different number of values here. But in this case, with this stride of 2, we are reducing the number of values. We start from 8, we end up with 5 because of the way we're sliding here combined with the padding that we have. So typically, if you have stride values over greater than 1, you will end up with smaller outputs than inputs. If you have a stride value of 1, you can end up with the same output as the input. But if you want to have a larger output than the input, then this won't work like this. You cannot get a larger vector here on the output than you have on the input. So this is where those transposed and fractional stride convolutions appear that allow us to upsample the inputs in this way. So transposed convolution works, you can imagine this as if you were transposing the orientation of the kernel and the way you're sliding it. So now we have the input there, x, but we are using the kernel here in the vertical, so to speak, and the kernel is supplying values to different parts of the vector, of the output vector. So the first kernel is going to be at 0, this is the padding here, the second two. The third one is going to be multiplied by the first value there and supply the first value for the y here, and the fourth will again multiply by that first value and supply the second here for the y. But then we slide the kernel, again with the stride of 2, and now these will add to the values that we already had in y. So basically we are doing similar things, multiplications and sums, but it's like we transposed the direction of the kernel, and now depending on the stride that we use, we can actually get more values on the output than we had on the input. So this is a way, this is called transposed convolution. It's a way of using convolution to increase the size of the maps, the feature maps, or the vectors that you have. Another possibility, this fractional stride convolution, is to increase the input by intercalating zeros between the values that we had, and then we can apply the kernel with a stride of 1. Depending on the numbers of zeros we are putting between the values, this will be analogous, we can imagine, as if we were using a fractional stride below 1, because we are taking longer to go through each value since we have all of those zero padding between. So this way we can create an output vector that is larger than the input. The input are only the white squares there, because we put all those zeros between the original values. So these are two ways of using convolution a bit differently in order to do the upsampling with the convolution. However, these have some defects. Because of the way the multiplications are done, some values on the output will receive more weights from the input than others, and you end up having these kinds of artifacts when you zoom in the result. So transposed convolution, these kinds of approaches, is not very good because of the kind of artifacts it creates. One better approach is to use upsample followed by convolution. This is an example in 2 dimensions. You can use this upsampling 1D or upsampling 2D, depending on whether you're working in 1 dimension or 2. And you can use different forms of interpolation. Nearest is just copying the nearest value, or you can use linear interpolation to make the average between the two. So you can imagine, if this was an image, you can imagine that we are increasing the resolution, for example, just by copying pixels. So we have the image in larger resolution, but now everything is also in squares, because we just, instead of having 1 pixel, now we have, for example, 2 by 2 pixels, but they are the same color. So the image is not better looking, it's just occupying more pixels. But now if we apply a convolution, the different weights of the convolution can help us focus the image better, and so this combination is what is doing the increased resolution on the image. First, just copying the pixels, and then applying the convolution to change them in a way that makes the picture higher resolution. And this works better because it doesn't have those artifacts that the transposed convolutions have. So this is the general approach. As we do convolution pooling, then when we go back on the decoder, we can do upsampling and convolution and intercalating. There are other alternatives. For example, use several kernels on the original input. but then shuffle everything or put all the feature maps, instead of putting them into different channels, you just alternate the values there and create a mosaic with the values from the different feature maps. However, this ends up being similar to what you can do with upsampling and convolution, and it's just a bit more inefficient to do computationally. So again, the upsampling and convolution approach seems to be better. But I'm just talking about all of these different approaches because you can easily find them in the literature or examples of using these different things. Just don't mix everything together, because there's no use in using, for example, a transposed convolution and then upsampling and then a convolution or something like that. That will be very confusing. And generally, this is the more intuitive approach and the one that seems to work better. So let's see an example of using these kind of convolutional autoencoders to create deepfakes. And this brings together some of the techniques that we saw so far. So what we want to do here is to transform the face of one person, for example, Jimmy Fallon, into another face, for example, John Oliver. So what we need is to create a representation of the faces in some kind of encoding, such that we can then recover the face here. But we need to find what is the appropriate representation for the face that corresponds to what we want to obtain. So one solution here is to train the same encoder on different sets of inputs, so that the shared space here is the same for the two faces, the two people, but then we train different decoders so that we output the image of one person or the other. And this is the general layout, in which we apply some deformation randomly on the faces. This increases the robustness of the autoencoder, and it's effectively increasing the data size. But we train the same encoder, and we alternate training a few epochs with Jimmy Fallon, create the encoding, and then the decoder part to recover the original image without this deformation. So this decoder is learning to start from an encoding obtained from the deformed image and correct any small defects it finds to obtain a good image. And now we alternate training the same encoder, but with the John Oliver images, also slightly deformed, but then coupled to a different decoder, the one that produces the original John Oliver image. And basically we have, both of these are autoencoders, but this part, the encoder, is shared between the two. It's the same between the two. And now, when we want to replace the images of Jimmy Fallon with those of John Oliver, what we do is we apply Jimmy Fallon images to the encoder. We obtain the representation, but then we use John Oliver's decoder to get the image from there. And now the John Oliver decoder is starting from this representation, but since this is the same encoder and it has been trained on both data sets, it has meaningful representations for Jimmy Fallon too. And so now we get John Oliver instead of Jimmy Fallon, but in the same positions, fixing the images in the same way. So this is an example of how to do deepfakes. This is especially easy to do for famous people because you can find lots of videos and photographs and so on for them. But this is one example, and it's fairly simple to train these networks and to apply this. This is actually online if you want to experiment. You need a fairly good computer, and it can take a few days to train the network, but it's not difficult to do this. So this is an example of using autoencoders to create a useful representation from which you can retrieve the data that you want. Another example is unsupervised segmentation. Remember last week we saw this UNet architecture for supervised segmentation, where we have images, we have in our data labeled images with the regions of interest. For example, if we have an image of a bug here, here we have a mask with the outline or the area the bug occupies in the original image, and we have lots of these images, so we can train this network to create the appropriate segmentation. This is what we're going to do in the assignment with the Pokemon images where you have those masks. But we can do something similar to this, unsupervised, by using an architecture that looks more like an autoencoder. We have here this is called a WNet, so it's basically two UNets architectures. But we have the original image, then we have an encoding here, and then we have the original image again. So this would be the encoder and the decoder. But we are training this part here, this encoding, by adding this normalized cut as a regularization term. So basically, if you imagine you have a graph, the cut for that graph would be for a partition of that graph into two subsets, A and B. The cut is the sum of the weights between all elements of A and all elements of B. So basically, it would be the weights you would need to cut in the graph to separate the two subsets. Since this is not easy to differentiate, we can use this normalized cut. Also, if we try to minimize this, the tendency is for one of the subsets to be just one node, because then you can minimize the amount you cut. But this would be the normalized version, or the normalized cut, where we have the cut between the two sets, and it's divided by all the weights between one set and everything else. So basically, this normalizes and removes the tendency to just take a bit from the graph, and it tries to look at the frontier between two subsets on the graph, where we can cut losing the smallest weight in total. Actually, this uses the soft normalized cut for differentiation, for backpropagation, but the idea is the same. And what we have here is that we define this cut here as weights between for example, the pixels. If the colors are very different, then we have a small weight. If the colors are very similar, we have a large weight. And so we are trying to create a representation here that divides the image into subsets. So each channel here is just either 0 or 1, for example, so subset A or subset B, and divides that by trying to cut where the pixels are more different and preserve together the pixels that are more similar. And we can have several layers here so that we have several of these cuts. And what happens when we train this autoencoder is that if we start, for example, this image of the airplane, we are going to create in the encoding different regions separating the image, because that both preserve the information necessary to retrieve the airplane from here, because the decoder must be able to reproduce the airplane, but also try to minimize that soft normalized cut, so they try to put similar pixels together and separate them from different pixels. And then after post-processing and clustering and so on, they can narrow down the different segments. So this is what you get on different layers of post-processing from the encoding of this WNet, that you can clearly distinguish different parts of the image and different objects. So basically, this is an autoencoder that is learning, because of the way we are regularizing the encoding, it's learning a useful way of segmenting the images without needing these labels to be supplied. So this is all unsupervised from the images. So other applications, one very useful is for manifold learning. This is just a review of what we saw last semester. So basically we have this manifold, which is a lower dimensional hypersurface, for example, where the data is represented. This would be an example of data in 3 dimensions, but you can follow it in 1 dimension, and you could get a very useful representation of this data just in one dimension. Last semester we saw methods like TSNE or ISOMAP for doing this, which are much better than things like, for example, PCA that don't try to capture these manifolds. But this is one application where you can use autoencoders, especially under complete autoencoders. For example, this is the exercise that you're going to do next week. This week there are holidays. So we have these banknotes data sets that you already used for classification. They are in 4 dimensions. If you use PCA and project them in 2 dimensions, you get something like this. The fake and true banknotes are pretty much mixed together. But if you train an autoencoder, this is an example with this architecture. So we have 4 dimensions here on the input. Then we put that into dense layers of 6, 4, 2, 4, 6, and then a layer of 4 at the end to reproduce the same as the input. So this would be the autoencoder that is trying to create a representation of 2 dimensions with 2 neurons that allows it to recover the positions of these points. And this creates a much better representation of the data. So one application of autoencoders, a very useful one, is for manifold learning. Of course, you need to be careful of overfitting, because if the encoder and decoder are very powerful, you can manage to recover the original data in your training set just by memorizing it on the decoder, and so the pattern of the encoding itself can be completely useless. If you are overfitting, the pattern may not be useful for anything. So you need to experiment with the dimensions of the autoencoder so that this works. Other application of autoencoders is anomaly detection. Suppose that you have some problem in which very rarely you have some anomaly. Things like you have logs for a server used, but sometimes things go wrong, or you have a machine that is creating some product, but sometimes they have defects. But this occurs very seldom, so it's hard to use supervised learning to classify and to predict when those things are occurring. But you can use autoencoders if you train the autoencoder with the good data, without the anomalies. Then the autoencoder becomes very good at reconstructing that particular kind of input. If something occurs that is not of the same kind, then the reconstructor error will be higher because the autoencoder is not prepared for those different inputs. So you can test for some kind of anomaly, even if it's very rare, by training the autoencoder with just the normal data and then checking the reconstruction error. When the reconstruction error is high, then probably this is something that is not like what the autoencoder was trained with. So this is another application of autoencoders. Okay, so to sum up, we saw a specific way of trying to find good representations of the data. These are the autoencoders. Basically, we want to learn on the output the same as the input. This would be trivial, but we are forcing the autoencoder to do something else. To reduce dimensionality, to reduce the derivatives, to reduce the number of neurons that fire, or those normalized soft cuts, and so on. So there are different things that we can do to try to coerce the autoencoder to do what we want. And that is the trick here. Whatever we do to pressure the autoencoder, that would give us something useful there in the encoding.